Good evening, everyone. I am Raver Joe the Asin, and today we're going to be talking about colligative properties. So, what are colligative properties? Colligative properties are the physical changes that happens to a solvent when you add solute into it. Changes don't depend on what kind of solute you add, but on how many you add. Colligative properties helps us understand how a certain amount of solute particles change the way a solvent behaves. In total, we have four main types of colligative properties. We have the freezing point depression, boiling point elevation, osmotic pressure, and vapor pressure lowering. I am going to be discussing the vapor pressure lowering and the boiling point elevation, while the other two will be discussed by the next reporter. So, let's start with what is vapor pressure lowering. Vapor pressure lowering refers to the reduction of the vapor pressure of a solvent when you add a non-volatile solute into it. Wait, that sounds very complicated. So let us break it down into its processes. So, for example, in a pure solvent like water, molecules at the surface have enough energy to escape into the gas phase. This process is called vaporation, and it creates vapor pressure, the pressure from the gas molecules above the liquid. But things changes when you add a non-volatile solute like salt or sugar into it. Those solute particles mix up and takes up space at the surface of the liquid. And since the solute doesn't evaporate, it just sits there, taking the place of some water molecules. The result? With fewer matter molecules at the surface, there are fewer opportunities for them to escape into the air. As a result, less water evaporates. And this causes the vapor pressure to decrease, or what we call vapor pressure lowering. To solve for the vapor pressure lowering, we use Rolle's law. And as much as I want to demonstrate how this is solved, I don't have the right equipment to show you the digital version of it. So instead, let us watch this video of a teacher on how she solves this.
Let's look at Raoult's law. P1 equals X1 P1 standard. Let's start by defining all of the terms in this equation. P1 is referring to the vapor pressure of a liquid in a solution, the liquid usually being the solvent of the solution. X1 referring to the mole fraction of the liquid in solution. Again, this is usually the solvent in the solution. And then P1 standard referring to the vapor pressure of the liquid if it were pure or when it is pure, not part of a solution. Raoult's law is handy because it allows us to actually calculate the vapor pressure of a liquid when it's in a solution, as long as we know the mole fraction of the liquid in the solution. One of the problems with Raoult's law is that it requires us to know the concentration of the solution in terms of the liquid, which is typically the solvent. Normally, when we express concentration of a solution, we express it in terms of the solute, not in terms of the solvent. So the notation is a little bit weird in Raoult's law, just in terms of how we are expressing the concentration. Let's see if we can make this equation a little bit more useful for us. In order to do this, we're going to be doing some algebra, and we are going to start by thinking about the change in the vapor pressure. So how we would define mathematically the change in the vapor pressure for substance number one. Again, in Raoult's law, we use the number one just to indicate one of the molecules, the solvent molecule. So the vapor pressure change, the delta means change, the change in the vapor pressure for molecule number one is going to be the difference between the vapor pressure of the pure liquid and the vapor pressure of the liquid when it is part of the solution. So if we just take the vapor pressure of the pure liquid and we subtract the vapor pressure of the liquid once it's become part of a solution, that gives us overall the change in vapor pressure for that particular substance. What I would like to do is take Raoult's law the way that is written right now. Raoult's law gives us a definition of P1. It says that P1 is equal to X1 times P1 standard. So I'm going to take this and I'm just going to plug it into this delta P equation. I'm going to, instead of writing P1, I'm going to use Raoult's law to write something different in this place. So I'm going to get the change in the vapor pressure for this molecule number 1. It is equal to the vapor pressure of the pure substance minus the mole fraction times the vapor pressure of the pure substance. Now, right now, it might not seem that we're doing anything useful, but just bear with me and you will see that this is about to get useful. I am going to do some algebra in the next step. So I'm going to see that on this side of the equation, I have P1 standard twice. So I'm just going to combine those terms. Again, just going to do some algebra here. And I'm going to get the delta P1 is equal to P1 standard times 1 minus X1. So I'm doing basically like the opposite of expanding. Now I see that I have this 1 minus x1 standard, and let's kind of pause for a minute and think about mole fraction. We know that if we have a solution that has two components in it, the mole fraction of one component plus the mole fraction of the other component always adds up to 1. If we had a solution that had three components, we could say the mole fraction of component number 1 plus the mole fraction of component number 2 plus the mole fraction of component number 3 would equal 1. However many components we have, all of their mole fractions always have to add up to 1. This is just a property of mole fraction. And so I could actually manipulate this a little bit. I could say, okay, the mole fraction of component number 2 is equal to 1 minus the mole fraction of number 1. So what I've done here is I've done some algebra. I've subtracted x1 from both sides of the equation, and that's given me this equation right here. So again, I'm going to take this term, 1 minus x1, and instead of writing 1 minus x1 in this equation, I'm going to write x2 in its place. So I'm going to say delta P1 equals P1 standard times the mole fraction of component number 2. And this is actually a much more useful form of Raoult's law. So I'm actually going to kind of move it and make it a different color, because this is typically the form of Raoult's law that we use when we're doing these types of calculations. And let's take a look at each one of these terms. So this delta P1, this is the change, or specifically the lowering of the vapor pressure of our solvent. P1 standard, we already have defined, is the vapor pressure of the pure liquid, which we usually know because we can look it up. And X2 is the mole fraction of our solute, which makes more sense because typically, as I said before, typically we express concentration in terms of our solute, not in terms of our solvent.
Now that we know what vapor pressure lowering is and how to use Raoult's law to solve it, let us now proceed with the boiling point elevation. The boiling point elevation happens when you add a non-volatile solute into a solvent, making it being able to withstand more heat as compared to the pure solvent alone. And that sounds so hard to get. So let us explain it, connecting it to the vapor pressure. So boiling happens when a liquid vapor pressure becomes equal to the atmospheric pressure. Basically, when the liquid pushes up with enough force to overcome the air pressure above it. But as you may know, when non-volatile solute is involved, it lowers the vapor pressure of a solvent, as we have talked about before. So fewer solvent molecules can evaporate, because solute particles takes up surface space. Now, because the vapor pressure is lower, it takes more heat energy to bring it up to the point where it matches the atmospheric pressure. In other words, the liquid needs to get hotter to boil. The result of this is the boiling point increases. This is called the boiling point elevation, and it is another colligative property. Just like the vapor pressure lowering, the boiling point elevation has its own set of formula that we use to determine how much heat it needs to heat up a solute with a solvent. So, in order to enlighten us more in this matter, let us watch this video so that in the end of it, we know how and what to do to determine the boiling point elevation.
In this video, I'm going to explain why adding a solute raises the boiling point of a liquid. And to do that, I'm going to be using a phase diagram. As a reminder, a phase diagram is a graph of pressure and temperature for a particular substance. The phase diagram shows us, for any given pressure-temperature combination, whether the substance is going to exist as a solid, or a liquid, or a gas. In addition to that, it shows us the pressure-temperature combinations where the substance is undergoing a phase change. So this line that I'm highlighting here represents all of the possible pressure-temperature combinations where the substance is converting from a liquid to a gas, or boiling. The boiling point of a liquid, the temperature at which the substance boils, is defined as the pressure-temperature combination that falls along this liquid-gas line and corresponds to normal atmospheric pressure. For most of us in the United States, normal atmospheric pressure is 1 atm. So if we wanted to know the boiling point of this substance, we would locate 1 atmosphere on the pressure axis. We would find the point along the liquid gas line that corresponds to that 1 atmosphere pressure, and then we would find the corresponding temperature. Let's do that. So we're going to start at 1 atmosphere. We're going to go across the graph, the phase diagram, until we reach the liquid gas line. And then once we reach the liquid gas line, we're going to go down and see what temperature corresponds to that particular pressure. So for this substance right here, what we have identified, whatever this temperature might be, this temperature is the boiling point of this particular liquid. We'll just say it's the boiling point of this particular substance. And we indicate this, capital T, subscript B for the boiling point. And we're also going to put the standard symbol on it, the degrees sign, or what looks like a degree sign. This indicates, again, same notation as we've used before, that this is the boiling point of the pure substance. Now, when we add a solute to a solvent, as we saw in the last video, this causes the vapor pressure of the substance to lower. The vapor pressure of the substance to lower. The vapor pressure is the point where the substance is in equilibrium between the liquid and the gas phase. And again, the pressure of the liquid-gas equilibrium lowers. So what this means, practically speaking, is that all of the points along this line get dropped down to a lower pressure due to the presence of this solute. So that liquid gas line gets redrawn a little bit lower, maybe something like this. And again, this is the line due to the presence of a solute. So the liquid gas line lowers because the vapor pressure lowers due to the addition of a solute. Because we lower the liquid gas line, we also change the boiling point of a substance. So once we've added this solute and we've dropped the liquid gas line, if we wanted to know the boiling point of this same substance, we would go back to 1 atmosphere again. We would do the same thing, trace our 1 atmosphere line across the phase diagram until we come to the liquid gas line, which is now over here. And then we would drop that down to find the corresponding temperature, which is now been raised. It is now over here. So this is the new boiling point, and this is the boiling point of the solution due to the addition of whatever this solute is. And we'll indicate that as TB without the degrees symbol because it's no longer representing a pure solvent. We can calculate the change in the boiling point of a liquid using an equation. The change in boiling point, delta TB, is equal to a constant, which we call the boiling point constant, capital K subscript B, times the molality of the solution. So Kb is a constant, and this is a constant that is specific to the liquid. It doesn't matter what the solute might be. So water has its own constant, benzene has its own constant, and you can look those constants up in a table. And then M is this is little m, so this is the molality, not the molarity. And this, again, this allows you to calculate the actual change in the boiling point, which is represented right here on the phase diagram.